Well, hello, sunshine. Getting ready to put this Poulan PR5020 back together, and I wanted to stop and let you guys know a few of the things I've done. I've made some videos along the way, but I'll be honest with you, this has took me a while to do these mods in, amongst other things. It's been wintertime, boo-hoo, poor pitiful me. But I haven't been hitting it that fast, right? And I don't remember what's all hitting the other videos, to be honest about it. It's been that long. So, we'll start with the cylinder. The first thing we did is took these bearing pockets down 55 thousandths, okay? And then we took this base down right here 55 thousandths. Essentially tightened up our squish. We started with a bunch of squish. We're down to 20,000 squish now. Matter of fact, we was with a stock piston, we was at less than 20,000 squish. Okay, inside this cylinder, I really haven't taken much metal out here and here. I've more or less just put a texture in there I wanted. Now where I've taken the metal from is, this used to be solid right here, up and down. I've cut these channels in here to allow air to get in there. It'll never show, but picture your mind's eye where these were. Those crank lobes, when you're at bottom dead center and starting to push that air, those crank lobes are in the way of getting air straight into those lower part of those transfers. So I tunnel them out. It's something I've done on 025s, MS250s, 29s, 39s, all the steel clamshells like that. It's where I found big power in doing that. So of course we're going to do it on this one. The transfers are very similar. Being a strato saw, and I wish I'd have took you a picture. I'm gonna, sorry guys, I just knocked that camera over. So I'm gonna reset. Now this being a Husky is still the same principle as a strato saw. So you got a flat surface right here. And there's your fresh air intakes, and there's your fuel air intake. And like I say, that's a flat surface that a manifold bolts to. I'm gonna move you one more time. I didn't get you set back right. That's a flat surface. Now here's a Husky cylinder, and I want to show you the concept because I don't remember if I got a video of this. But this flat surface right here is where your manifold bolts to get fresh air here and here and fuel here. Well, this Poulan was substantially similar. It was a little different shape, but that was flat across here. And there was a big divider in here to keep all that separate. Well, you can see we've taken all that divider out there, okay? So we're gonna dirty it up, whatever you want to call it. It's gonna get fuel air in there, and I've changed the port timing a little bit on the intake, which we're okay, and I've changed it on the Stratos too. You can see on the inside here that intake hole. I wish I'd have got better pictures before and after, but I didn't. I had a guy the other day text me. It was in the comments saying, "Hey, would you show more of what you're removing?" This is the first video I've made since then, and it'll probably be 3 months after his comment before this airs. So I'll try to show you what I'm doing. I got the surface that I want here. I removed in the corner of that cylinder right there. I have elongated and made that hole bigger for the fresh air, for where the fuel air went on the saw. And if you'll look above those transfer ports, I've cut up on them a little bit and made boost ports out of those transfer ports. Now on top of that, of course, we've done the exhaust here, and I raised the exhaust a little bit and widened it. It's pushing 68% probably. And we'll probably end up going farther. I'm changing so many things at once on this saw, and I've not done one of these to that point yet to know, okay, here's all I need to do. I'm changing so many things on that saw that I don't want to raise the transfers and find out they didn't need raised and things like that. So, like I say, we took 55 thousandths off of this. which left us about a negative 12 thousandths squish, meaning I took so much off this, my piston wouldn't go to top dead center. The piston was 12 thousandths too tall. So I took 32 thousandths to get 20 thousandths squish off the edge of this piston right here. And then cut that at about 37 degree, and we put us a pop-up in there. So we're at 20 thousandths squish with a pop-up. Now I've taken the inside of this piston and I've massaged them corners just a little bit, and partly it was to get rid of weight, and partly it was for airflow and put texture on there I wanted. I don't know that the texture is important under there. You guys let me know. I thinned this exhaust side skirt a little bit. I left the intake side intact. That's where all your pressures, that's where, I wouldn't say all your pressure, but that's where most of your pressure is at on the downstroke, is this pushing that intake side against that intake cylinder wall. So you want some bearing surface in there, and that skirt needs to be substantial to hold that piston from breaking that skirt off. Now we did cut us some more intake timing on this intake side of this skirt. That was flat across the bottom, or it followed this radius. We took that much intake timing out of it, and we'll get to that here real shortly, because that's way too much for a regular saw. Okay, we're building us a Sawfest fun get-together saw. We've lowered the intake here, and plus we've took some intake here, and I'm not sure what that number is, and I'm going to talk to you when I get this put up and give you some stuff. I'll talk to you on some theories on what I'm having here, on what I'm doing, and that'll probably be the next video. So but that's about where we're at right now. Now we took that piston down. We took that piston down from 75.11 grams. That's how this piston started out. And I made it down to 70 point. Let me back up. I forgot to mention, I took these pockets here a little deeper too. And there's a purpose for those pockets on a strato saw. And this also has a piston pin that doesn't go all the way through. It's not hollow all the way through. It's got a divider right in the middle of it. That's important for a strato saw too. But I deepened these pockets up a little bit. Part of it to save weight, and part of it because I think that might help my flow a little bit. Even though they're dead-ended and don't go anywhere, there's a reason for them. We might have already talked about it. If not, we'll talk about it later. Or if you know what it is, put it in the comments. Try not to get too long here. But I deepened those up, took this off here on the intake, took part of the top off, took 32 thousandths from here to here is basically all I took off there for weight, so not much there, and lightened up on the inside of it a little bit, and I got down to about 70 point. I was a half a gram short of 70, and I don't know, my mind clicked and said, well, you need to be below 70. So we took everything off a little bit more and got it down to 69.98 grams. All right, now why do I say that? Why do I care exactly what that is? Well, it's inertia force. This piston, when it goes to top dead center, this piston and part of that rod, this crank bearing right here sees that as weight. It's inertia. It's flinging that out. This has to stop it and change direction. That's a lot of force on the bearings. It's a lot of force on the rod. A lot of force on this journal. The piston itself's a lot of force on this piston pin, right? How much force, you ask? Well, you can calculate that, and I did. So I'm going to give you some numbers here, and we're going to talk about them in just a minute. I got them wrote down because, well, they're numbers, and if you want to write them down, they're hard to understand just hearing them probably. I'm probably not very good at putting the information out there in a manner that's going to stick in your mind. Don't try to remember all the numbers necessarily, unless you want to. I just want you to see some correlations. On the initial weight of this piston at 75.11 grams at 10,000 RPMs, it had an inertia force of 305.49 pounds. If you want kilograms, divide that by 2.2. At top dead center, it had an inertia of 383.31 pounds. At bottom dead center, it had an inertia of 227.67 pounds. That's at 10,000 RPMs, right? So let's say inertia force at top dead center was 383 pounds, which it was. That means this these bearings are holding 383 pounds. That's like putting this in a stand and hanging 2 big men off of it, or whatever, 300 and something pounds off there, hanging more than a full-size hog off of it. Butcher hog's only 280 pounds, so you're holding the whole butcher hog off of this bearings right here, and this rod, and this these bearing surfaces inside this wrist pin, all that. You're holding 383 pounds at 10,000 RPMs, okay? Due to inertia. Well, we're gonna go with the big number, and I'm not gonna compare a bunch of numbers, but realize the top dead center inertia force is your biggest force. By taking, we was at 383 pounds on this stock piston, and by taking off down to 69.98 grams, try not to put too many numbers in there, we went from 383 down to 357. So we lost, quick math, dirty in my head, 26 pounds. We lost 26 pounds off there, and you think, well, that's not too substantial, and it kind of isn't, but it kind of is. In order, I can now, and I want, it kind of is, because I want to change this to what it feels at 12,000 RPMs, okay? Originally, this saw at 12,000 RPMs had 552 pounds of pressure at top dead center. Feeling it on that rod again, right? We got that down to 514 at 12,000 RPMs by lowering this weight of this piston. It dropped 35, 36 pounds, 37, it dropped 37 pounds what it dropped. You think, well, that's not that much, but you remember a minute ago where we was at 10,000 what the number was, and now we're at 12,000 what the number is, right? I'm gonna sidetrack just a minute and see, like this saw and some of the like let's say a Husqvarna saw X-Torque that went from using one case and changing it to a strato saw and put a heavier piston in them. That's why they put a rev limiter in the coil, is to keep this inertia force down on this piston. They just put a heavier piston in there and their bearings wouldn't take it anymore, so they used the same case and the same bearings. So what are they going to do to be able to make those take that force? Lower the RPMs. They tie to each other. The RPMs go up as they tie to each, so they tie to each other. As the RPMs go up, your inertia force goes down or up. So how do they combat that? Well, they can put a lighter piston in. We can lower the RPMs, right? Put better bearings in. Well, we're stuck with a piston. We're stuck with the bearings and the crank and the rod and all that. So if we want more RPMs with the same force, we are better off to lighten this piston. We were just able to gain 390 RPMs on this saw, meaning this original piston had 551.97, 552 pounds of inertia force at top dead center at 12,000 RPMs. When I lightened it up, now we hit 552 pounds of inertia force at 12,390 RPMs. We just put 390 free RPMs without that rod, without that rod, this piston pin, the bearings. It doesn't think we changed anything. It doesn't know we increased 390 RPMs. It's happier. It thinks we're the same. And there's other benefits too, but I wanted to talk about inertia force because that's a great big thing. You go to increasing RPMs, you're drastically changing inertia force on this piston. So you need to think of some way to combat that. You figure the engineers, it's common practice, there's common knowledge, common thought that they put about 20% when they design something, and they think that, well, there's going to be X amount of inertia force on here. They incorporate 20% overbuild in it. They'll want a bearing that's 20% over that, that'll handle 20% over that. So you can get away with doing some stuff, and you're pushing closer to how fast you're going to wear that bearing out and how fast you're going to tear things up in there, and what the saw for which is designed. But if you can lighten that piston, from this piston down, that saw really doesn't know any difference, argumentatively. So what I'm going to do, I showed you basically what's in it. I'm going to put this together right quick, put the crank in it, seal it up, get it stuck together, and I want to show you this intake block and basically to where we're at right now and explain to you a couple more things that's coming up. Well, we got most of the main part ever glued back together. We got the clamshell bolted on and bolted down in the case, and we got our intake block bolted on there. And you can see we've hogged out them transfers we can hog that intake out pretty good, and we've dirtied it up. You guys may be interested to know what the numbers are. I'll try to flash up a picture on the screen in case you want to write them down. But I'm going to tell you I'm going to give you 3 numbers, and I'm going to go through it quick, just because I don't want to drag it out. If you want to write down the numbers, go through it a little bit at a time or write them down. I'm going to give you 3 columns. We're going to go with stock, what we was stock. Then when we lowered it 50 thousandths and done the piston work, we ended up at another set of numbers. And then when I ground on the cylinder, we wound up to the 3rd set of numbers, okay? Stock, and I'm not gonna look at you because I gotta read it. I don't know what they are off the top of my head. Stock, we was at 38,000 squish. We made it down to 20,000 squish with the piston work. It didn't change with the porting. So we're still at 20,000 squish. Stock saw was 111 on the exhaust. As soon as we did the piston work and dropped the cylinder, we wound up at 112. And we was at about 56% of port width was 56%. We raised the exhaust, we're at 105 now and pushing 70% of diameter. The intake, we started out at 70 degrees for 140 degrees total opening. After we lowered it, we wound up at 74 degrees for 148 degrees of total opening. Now, we ground on the intake and we ground on that piston. We wound up with 102 intake, 204 total opening. We'll get to that. We got us a plan. We got us a problem, but we got us a plan, and the problem's easily to figure out. I just got to make a decision. Now, the strato intake timing is tied in with that piston too, right? Especially when it's stratified and not dirtied up like this. But it still makes a difference when they're dirtied up, because if your intake below the piston opens before your strato port opens on the side of the piston, there's case vacuum inside the strato ports and the lower case. It's all under vacuum. So when you open one up first, you relieve part of that vacuum by filling that in maybe under the piston. That's where you can get into trouble, just changing one and not changing the other. We did change one and not change the other much because we're dirtying them up. But my intake is going to open now at 102 degrees, but my transfers before they were 4 degrees separated from the factory. Stock intake opened at 70, but the transfers opened, or the stratos opened at 74. So when I dropped it, then the intake opened at 74 and the stratos opened at 78. Well, now we're still opening the stratos at 78, and instead of opening the intake 4 degrees earlier, we're opening at 102, which is 78, that's 24 degrees earlier. So those stratos aren't going to pull as hard than they would have. They're just not going to pull as hard. It wouldn't bother me if they did, but they're not. So we went from 74 to 78, and then we stayed at 78 because I did not grind on the piston. That's just where it wound up. Now, we started out at 125 on the transfers stock. When I lowered the cylinder, it went to 126. Guys, I don't know. So that was 14 degrees blowdown. Well, I don't know how much blowdown I'm going to need. And I know I changed the exhaust. And, of course, we're getting really goofy right here. So I don't know how it's going to change my needs. And as much as I want to reshape those upper transfers right now, I haven't touched them. I textured them, did not touch them. they're still at 126, just like when I did the machine work. But we went from 14 degrees of blowdown at the machine work stage to 21 degrees of blowdown now. I'm hoping I get to change that blowdown and maybe go a little less. I'm hoping this saw will want less. And the reason I'm hoping that is because I really want to change the shape of that upper transfer and change that aim a little bit. I'm nervous to do that yet, and I can't put it back in there. And there's a set of micro ports in there that weren't in the other two. Those micro ports open at 121 degrees. They're kind of like finger ports, but not really. And so there's 16 degrees of blowdown to the finger ports, micro ports. They're separated out 5 degrees from my upper transfers. Hopefully that's not too much, but the port time duration, port time area, I guess it's called. They're pretty small, rounded at the top, and I took the total opening, or where they cracked open. The actual dynamic difference in blowdown probably won't be 5 degrees. But I want to put this all together and get it running. Now, what's the problem I talked about? Well, that's where I want to draw my impulse from, and if I want to change my intake timing any. The piston port of the intake is 102, right? So 204 degrees duration. The reed block can actually supply more than that, right? It can supply 180 degrees of intake duration, can it? Or intake pull. We can get as much intake duration as we want, but I'm still using the piston ported part, okay? So when that piston's coming down 102 degrees after top dead center, which is way later than what the original intake timing was, right? We went from 70 to 102. We gave it 30 more degrees in the piston port, which would not run worth a hoot if it even run at all. But we've got the reeds on there, okay? Now, why didn't I just open that all the way up farther? Well, a couple different reasons. I wanted some bearing surface on my face of the piston, on the intake side of the piston, so I only opened it up some, and I can open it up more if I need to. But this case compression, when it starts compressing, this whole reed block and this whole assembly has now become part of your case volume, hasn't it? Now, instead of just compressing that little area under the crankshaft, we're compressing this whole area. So, when we get down to 102 degrees now, we change from compressing this whole area, and it blocks this off, removes that from case volume, leaves a little bit of pressure in here, but the last, what would it be? The last 78 degrees all the way to bottom dead center is only compressing then. Once in, I lower my case compression at 102 degrees, I change my case volume from all this to what's under here. That's my mindset. Tell me if I'm screwing up. Now there's still gonna be some pressure up here, and that's what's gonna feed my micro ports is out of this. And if I get exhaust flow back through my micro ports, it's gonna foul this charge, but it's not gonna foul plumb to my bottom end, if that makes sense. We may wanna change it. We may wanna open that piston up, but why does that bother my, why would you say, well, why is that bothering your impulse, right? Well, if I run some funny fuel in this and I'm trying to get that through a carburetor, I might need a bunch of impulse, right? I might need a full impulse. And impulse works on case compression. Maximum vacuum to maximum case compression is the difference in your impulse from one side to the other, right? Well, I will actually have a greater case compression inside the case than I will out here. If I run my impulse out here where it's easy to get to, I can just drill into the side of this block anywhere I want, put me a fitting in there. I could drill into here anywhere, put me a fitting in there, and I've got my impulse. But I think I will get a stronger impulse inside the engine, not on this reed block. So there's a problem. So, and it's not a big problem, and I just got that setting on there. I'll put studs in that later on. But the point of it is, I can, not like that Husqvarna I built where I messed that up to where you got to take the cylinder off, change it. At least this in here we can change. We'll put some studs in there and get reed blocks, and I got some material here. I can either run this big carburetor, probably build me a flat plate for it here, and I'll probably start off with just chainsaw type carburetor on this reed block setup. And I can change to a different reed block setup. I've kind of got this, I don't know what I'm doing, guys. I've just got this to where I can change it as I go. So I think we're gonna call this video. We're probably 20, 30 minutes in, so I'm gonna wrap it up. There's where we're at right now. Guys, if you enjoy this, guys, I just hope you enjoy it. That's just all there is to it. You guys can do all that stuff down there in the bottom. Helps the channel, helps me. Love talking to you guys. But if you ain't in the mood, just don't do it. Appreciate you being here, I really do.